Hey there! I've been involved in front-end development for 15 years, and during this time, I've seen JavaScript evolve from being considered a simple, silly scripting language to becoming essential for building full-fledged SPAs on the front end and complex REST APIs on the back end. The JS ecosystem is constantly changing, and this rapid evolution can overwhelm many of us. Even worse, developers from different backgrounds are often discouraged to try front-end development because of the seemingly unnecessary complexity in this space. But the reality is that once you fully understand the basics, you'll realize that all these front-end frameworks have more in common than you might think. With this course, you'll identify common patterns and mechanisms that are shared by all modern frameworks, and once you master these concepts, you'll be able to confidently tackle front-end projects in any framework. I'm also a big believer in pragmatic, no BS approaches, so the next 90 minutes will be filled with concise, relevant information so that you'll gain the most value possible in the shortest amount of time. Without further ado, let's jump into it. The general architecture of a web app has a few main components. The user opens the browser, types in a domain name, and presses enter. The domain name system, or in short, the DNS, is then used to find the IP address of the server associated with the domain name. Then, an HTTP GET request is sent over the network to that server. In web dev terms, this is known as the backend, and it is an entire beast on its own. This is where you'll have either a server monolith, meaning one big server handling all business logic, or a cluster of microservices written in a variety of languages. Most of the time, the backend will also contain a data layer, which can be anything from an SQL database to a document-based NoSQL solution. Web servers have routing mechanisms, which will capture the incoming GET request, perform various internal logic, and return a response back to the browser, also known as the client. The client is what we'll focus on in this course, but before doing that, let's spend a minute reviewing the HTTP protocol in more detail. When the request leaves the client, it usually contains the following information: the actual URL or resource you are requesting from the server, a verb or method which describes the type of action you want to perform on the server, a list of headers which are key-value pairs providing additional information about the request or the client itself. Some examples are the user agent header, automatically sent by the client with browser and operating system details, or the authorization header used to send authentication credentials to the server. And, finally, if the method allows it, a request body with additional data sent to the server. When sending a request body, a content type header indicating the media type of the resource should also be specified. Note that GET requests explicitly do not allow a request body, while delete requests typically do not use a request body, even though they are technically allowed to include one. The HTTP response will contain the following information: a 3-digit status code indicating the result of the request. These are grouped by the first digit and could represent a successful action, a redirection, a client, or a server error. Response headers containing additional information such as the content type and the response body. While this communication is reliable and straightforward, it has a major flaw. The data exchange is done via plain text. This means that anybody sitting on the wire between the client and the server can easily read all our communication. This poses a significant risk, especially when the client sends to the server authentication, payment, or personal information. To address this flaw, the industry adopted HTTPS, which ensures that communication between the client and the server is encrypted, authenticated, and secure. HTTPS builds on the HTTP protocol by adding a layer of encryption via secure sockets layer and transport layer security, mitigating the risks associated with transmitting sensitive data over an unsecured connection. In practice, when a client initiates a connection to an HTTPS server, a process called the TLS handshake begins. Then, the client sends a client hello message listing supported encryption algorithms. The server responds with a server hello message, selecting an encryption algorithm and providing its certificate. The client verifies the server certificate, and both parties agree on a session key to encrypt further communication. Once the handshake is complete, all data exchanged is encrypted using the agreed-upon key. So even if a malicious actor intercepts the communication, the encrypted data is unreadable without the encryption keys. There is a wide range of response types you could receive from the server, but when working with the front end, you could expect the following: HTML responses describing the layout of web pages, JSON or XML files usually sent as responses from REST APIs, JavaScript and CSS files, static assets like images or videos. Back to our client, when we first access a web page, if the resource exists on the server, we'll get an HTML as the initial response. The file starts with the doc type declaration, followed by the HTML structure, which has two main sections. The head usually contains the title of the web page, a list of meta tags providing additional information required either by the browser or by search engine crawlers, and links to scripts and style sheets. The body contains the actual content, which will be visible to the user, ranging from headers to paragraphs and images. You can also link style sheets and scripts in the body, but this is usually discouraged. Once the document is received, the browser will go through a few steps to convert the HTML tags into the actual visual representation we are used to seeing in the page. The first step in the process is to parse the actual HTML elements. This is a synchronous process where the document is traversed line by line, and the markup details will be used to construct the document object model, or the DOM. The DOM is an in-memory tree representation of the document structure. Following the same approach, the browser will parse the CSS present in the page and will construct an associated CSS object model. Then, these two models are combined into a render tree, which includes only the elements that need to be displayed on the page. In the layout step, also known as the reflow step, the browser will calculate the position and size of each node in the render tree. Finally, the render tree is traversed and each node is painted in the correct order. Remember that efficient construction and traversal of the render tree are crucial for web performance, and that large, complex DOM structures can lead to slowness. Another important aspect is the way script tags can block the rendering process. Our example contains links to 3 resources: a CSS file, a JavaScript, and an image. When the browser encounters these resources, it sends additional requests to the server to retrieve them. While images are loaded asynchronously and do not block rendering, CSS files can delay the rendering process until they are downloaded and parsed to avoid displaying unstyled content. However, JavaScript behaves differently. Because JS can modify the structure of the document object model and the CSS object model, the browser must pause the HTML parsing process, download the script, and execute it before continuing. This blocking behavior occurs with synchronous scripts, which are the default. Once a synchronous script is downloaded, the JS code is executed immediately. During this time, the rendering of the rest of the page is simply paused, so large JS files can significantly delay the rendering process. If you want to avoid blocking the rendering process, you could use the async or deferred keywords. Both will trigger the download request on a separate thread. However, async scripts will be executed immediately after the response is received, potentially interrupting the parsing process, while deferred scripts will be executed only after the HTML parsing is complete. Traditionally, web apps are following a multi-page application architecture, or in other words, they are server-rendered. This means that whenever the user requests a web page, the server will compute the static HTML and will send it back to the browser. The browser will simply display this content and, if JS scripts are present, will load them up to add interactivity on the page. While this approach is straightforward, it has a few key characteristics which might be problematic. First of all, each user action requiring navigation triggers a full reload of the browser, even if only a small portion of the page changes. Second, every request involves server-side processing, which can be resource-intensive for highly interactive applications. As a consequence, the single-page application architecture emerged as an alternative to address the limitations of MPAs for modern interactive applications. In an SPA, the server sends a single HTML file to the browser during the initial request, along with the necessary CSS and JavaScript files. Most of the time, the HTML simply contains an empty app shell and links to JS scripts. Once this file reaches the browser, JavaScript takes over and manages both the content rendering and the navigation directly within the browser. Instead of requesting a new HTML page for every interaction, the SPA communicates with the server using APIs, such as REST or GraphQL, to fetch or update data in an asynchronous manner. Most of the time, it will receive JSON data in response, which will be used in the JS logic to dynamically update the content on the page. So, to reiterate, multi-page applications are server-side rendered, while single-page applications are client-side rendered. Another important rendering strategy is server-side generation, which takes a hybrid approach, combining the benefits of server-side rendering with some of the dynamic capabilities of client-side rendering. SSG involves pre-rendering HTML pages at build time. This means that during the deployment process, the server generates static HTML for each page, and these files are served to the browser as is. Since the HTML is pre-computed, users experience extremely fast load times, as the browser doesn't need to wait for server processing for each request. This makes SSG particularly well suited for content-heavy sites like blogs or marketing pages where the content doesn't change frequently. However, one limitation of server-rendered or generated content is its lack of flexibility for dynamic updates or interactivity. To address this, developers often pair SSG with client-side hydration, a process where JavaScript takes over a pre-rendered page after it loads, enabling interactivity and updating dynamic data on the client side. Another closely related strategy is incremental static regeneration, which allows pages to be pre-rendered statically but regenerated on demand after the initial build. This means that even static pages can have dynamic updates without requiring a full rebuild, enabling developers to balance performance and up-to-date content. There is not a one-size-fits-all solution when it comes to choosing the best architecture. Your use case will dictate if your application is rendered by the client, the server, or a combination of both. We'll explore this further in the upcoming chapters. HTML and CSS might seem basic, but mastering their fundamentals is essential. A solid understanding of semantic markup and styling principles will not only help you build well-structured, visually appealing interfaces, it will also set the stage for more advanced topics down the road. Don't worry, we'll go quickly through this chapter, since in real projects you'll probably work with component libraries which handle a lot of the HTML and CSS for you. HTML provides the structural foundation of a web page. Think of it as the skeleton that holds all your content together in a logical and meaningful way. CSS, on the other hand, defines how that structure should look. It's the layer that brings color, typography, spacing, and layout to your page, turning raw HTML into a polished, user-friendly interface. Every web page starts with HTML. At its core, HTML consists of elements represented by tags, which usually come in pairs as an opening and a closing tag to wrap content. In the most basic form, an HTML document will contain a document type declaration telling the browser we are using HTML5, an HTML element that wraps the entire page, the head containing metadata and references to external files, and the body which holds the content that appears on the screen. What's really important for you to understand is the relevance of semantic HTML. HTML provides abstract wrapping elements such as divs and spans, and in theory, these are more than enough for you to build any layout you want. However, the HTML standard comes packed with a rich set of tags that actually convey meaning. These will help you better organize and maintain your code while providing more information to robots and search engine web crawlers. So you can use headers to define a top section of an area, footers to mark the end of an area, navs to indicate a block of navigation links, the main tag to highlight the primary content of an area, section and article to group related content into logical units, and aside elements to define supplementary content like sidebars, pull quotes, or related links that aren't part of the main narrative but provide valuable context. Using these elements will make your HTML more than just a collection of boxes. The HTML becomes a well-structured document that communicates purpose and hierarchy. Assistive technologies, like screen readers, use these cues to help users navigate and understand content. Search engine crawlers also understand semantic markup, which can lead to better indexing and potentially improved search rankings. On top of these presentational components, HTML also includes elements designed to add interactivity and enable user interaction. While HTML alone doesn't provide application logic, it does offer structures that, when combined with CSS and JavaScript, can create the interactive user experience common to modern web apps. One fundamental aspect of website navigation is the link element. By placing A tags within your HTML, you can guide users from one page to another, effectively connecting your entire site into a cohesive experience. Links allow you to stitch together multiple HTML pages and resources, turning a collection of standalone documents into a well-connected application or site. Beyond simple navigation, another core building block for interactivity is the form. Forms enable you to collect user input, send it to the server, and process it, whether it's a search query, a feedback form, or user registration data. Inside forms, you'll find elements like text fields, checkboxes or radio buttons, drop-down lists, multi-line text inputs, buttons that submit the form or trigger other actions. Going back to the previous web app diagram, links and forms trigger HTTP requests to the server. Links will always trigger GET requests. The browser is in a blocked loading state while the response is received, and then the received response will simply be displayed in the browser as a new page. Forms, on the other hand, provide more flexibility. By using the method attribute, you can instruct the browser to send data and trigger a variety of request types. Common methods include GET for simple data retrieval and POST for creating or updating data on the server side. While GET requests append the form data to the URL as query parameters, POST requests send the data in the request body, allowing for larger, more secure transfers. This difference between links and forms highlights the growing complexity of how browsers handle user actions. Traditional navigation based on clicking links and loading new pages works fine for static sites or simple applications. However, as web applications grow more interactive and data-driven, relying solely on full-page reloads becomes inefficient and cumbersome. Users expect smoother transitions and real-time feedback, which leads us naturally toward the use of JavaScript and its ability to fetch data behind the scenes, manipulate the DOM, and update the page dynamically without full reloads. But before discussing JavaScript, let's look at CSS. At its simplest, CSS works by attaching style rules to HTML elements. These rules define how elements should appear on the screen, including details like font size, background color, margin, and padding. In practice, the plain HTML page on the left can be easily enhanced with just a couple CSS rules. The easiest way is to define the rules directly in HTML, but by separating content from presentation, you gain flexibility, easier maintenance, and the ability to adjust the design without altering the underlying structure. So while it might seem convenient to attach the CSS rules inline directly to the target element, the best approach is to extract all rules and use more general selector rules to define the visual attributes. This can be done either as internal styles defined in a style tag inside the head section of the HTML or as external style sheets linked via the link element. CSS rules typically consist of two main parts. First, you define a selector specifying which HTML elements the styles should apply to. Note that there are various CSS selectors that can even be combined, so you have a lot of control over the elements you want selected. Then you have a declaration block enclosed in brackets containing one or more rules. In a practical example, if two buttons share the same style, you should extract those rules and define them in a more general way. There are multiple approaches here. You can be very abstract and style all buttons on the page with a general rule. You can define a class of buttons and style them accordingly, or you can be very exact with your styling and identify specific buttons via the ID tag. What's more interesting is that you can extract shared rules in different blocks to streamline your CSS and avoid duplication. This is where concepts like the cascade and inheritance come into play. By leveraging these, you can define base styles that apply to multiple elements and then override them where needed. For example, if all your buttons share a common set of styles like border radius, padding, and font, you can define these properties as a general rule. Then, for specific buttons that need additional customization, you can use classes or IDs to add more specific styles. So general rules will cascade down into the more specific rules, which extend or override the inherited rules. The beauty of CSS lies in this layered approach. Rules are applied based on specificity and importance. If two rules conflict, the more specific one wins. Specificity is an algorithm that calculates the weight that is applied to a given CSS declaration. It is determined by a combination of factors based on the type of selectors used, with each selector having a specific weight. In a practical example, let's consider a very basic HTML and the following CSS rules. Here's how the rules apply. First, all button elements will inherit a font size, padding border radius, and default background color. Then, class-specific rules will be applied, so the default background and text colors are overwritten by the primary and secondary classes. Finally, the ID-specific rule has the most weight, so the red background will override all other rules for the submit button. Remember that when styling complex applications, specificity can become a challenge, and combining rules and advanced selectors can drastically change the precedence of your rules. In CSS, every element is represented as a rectangular box. Understanding the box model is crucial for controlling your page's layout and spacing. There are 4 key aspects you should be aware of. The content box is the area where your text and images appear. Padding is the space between the content and the element's border. Border is the line surrounding the padding and content, which can be styled or made invisible. And margin is the space outside the border, separating this element from adjacent elements. By adjusting these properties, you can fine-tune how elements are spaced and arranged on the page. HTML elements come with a default display value, which defines how they are laid out in the flow of the document. Most elements are block level by default, occupying the full width of their parent container and starting on a new line. They stack vertically, and margin, padding, and border values are applied on all sides. Alternatively, you can use inline level elements, which flow along with text, only occupying the space dictated by their content. Inline elements don't start on a new line and handle vertical spacing differently. As a result, inline elements are ideal for styling small pieces of content within a paragraph, such as highlighting a word or making a link appear inline. Of course, you can change the display value of any element with CSS. Beyond these foundational concepts, CSS offers more powerful layout tools that simplify the process of arranging elements on a page. Technologies like Flexbox and CSS Grid allow for more sophisticated, responsive layouts without resorting to CSS tricks and hacks. Flexbox excels at distributing space along a single axis, either horizontally or vertically. CSS Grid, on the other hand, provides a two-dimensional layout system that can define rows and columns, enabling complex layouts that adapt gracefully to different screen sizes. Today's users access the web through a wide array of devices: smartphones, tablets, laptops, and large desktop monitors. Ensuring your designs look great everywhere is known as responsive web design. CSS provides tools such as media queries, allowing you to apply different styles depending on the viewport's width, height, or resolution. Alongside media queries, you can use relative units to make your layouts fluid, ensuring that content adapts naturally to different screen sizes and orientations. With these tools, you can create sophisticated, flexible layouts that look and feel right regardless of the user's device. Responsive design is a key expectation in modern web development. As you incorporate more CSS into your project, keep in mind the importance of performance and maintainability. Large, unorganized style sheets can slow down the page rendering process and make it harder to maintain the codebase in the long run. So you should consider compressing your CSS files and reducing the number of HTTP requests to improve load times. Use approaches like block element modifier or other naming conventions to maintain clarity and consistency across your styles. Regularly checking your site on different screen sizes and browsers to ensure a consistent high-quality user experience. Note that there are a huge number of CSS rules you can use to style your content. The decision not to dive deep into all these options is a conscious one. On one hand, this is beyond the scope of this course. On the other hand, the reality of modern web development is that most of these rules can be easily deduced either via tools like Figma or AI coding assistants. JavaScript is the backbone of front-end interactivity. It's what turns a static web page into a dynamic, engaging user experience. When you are clicking on a button and a modal pops up, or you are typing in a search box and the results immediately appear in a dropdown, JavaScript code is running in the browser to make these interactions possible. So unlike HTML and CSS, which handle structure and style, JS is all about behavior. Remember that JavaScript is the only programming language that runs in the browser. There are two aspects worth mentioning here. First, we'll discuss later in this course about TypeScript, which is the go-to language for building modern web apps. However, TypeScript is compiled into plain JavaScript, which is then run in the browser. Second, WebAssembly allows you to run other programming languages like C++, Rust, or Go in the browser, but in such cases, JavaScript will still remain a bridge between assembly and the DOM or browser APIs. Okay. The good news is that most of the theoretical part of this course is over and, moving forward, we'll spend most of our time coding. In order to actually start writing some code, we need to set up our dev environment. Of course, you will be needing Node.js locally. Node.js will provide the runtime environment for executing JavaScript outside of the browser. It also comes bundled with a package manager called npm, which we'll use to manage dependencies and install tools that streamline the development process. For the IDE, Visual Studio Code does the job pretty well. In modern web development, your apps will be composed of JS files, modules, and packages which have to be bundled together into a single distribution.js file, which is served to the browser. V8 is probably the best tool to handle this workload, especially since it provides a seamless dev experience. So let's go ahead and run the npm create v8 command to set up a new app. There is a small CLI wizard you'll go through, and we'll choose a vanilla project using plain JavaScript. Note that V8 comes packed with support for various project starters, so it is going to be easy for you to start a TypeScript-based Angular project if you want to. Once the command is completed, you'll end up with this project structure. The next thing we'll do is to run the npm install command inside the newly created folder. This will look for the dependencies defined in package.json and install any needed third-party libraries inside the special node modules directory. Then, you'll see that V8 provides a handful of useful scripts, and we can execute the npm run dev command to start our dev server. This will start a Node.js process at the 5173 port. When you make a GET request to that server, the index.html is served to the browser. The HTML page is then analyzed, and all linked JS scripts are also requested from the server, downloaded, and executed. Let's start things easy by creating a simple counter app. The first thing we'll do is update the index.html page with the needed HTML markup. Inside the body tag, I will add a header which has a default value of 0 and a button to increase this value. Note that these tags are defined before the JSScript tag. This is important because when the JS code is executed, it will look for these elements in the DOM. If the script was defined before the HTML tags, the elements would not have been present when the JS code runs. So let's imagine for a second how we would implement this in the classical multi-page application architecture. Well, when the button is clicked, a new GET or POST request should be triggered on the server would update the counter value, and it will return a new HTML page as the response. The browser will be in a loading state until the response is received, and then will load the new HTML page, executing the entire HTML and JavaScript again. This is a lot of overhead for a pretty basic task. The alternative is to jump into the main.js file and perform these updates directly in the browser. The first thing we'll do is grab a hold of the two DOM elements we need to work with. The query selector method allows us to identify elements based on unique identifiers, classes, or even tag names. Since we have only one of each element on the page, grabbing them by the tag name will work just fine. Then, each DOM element can listen for user-generated events. These events can be mouse clicks, mouse movements, keyboard strokes, or touch gestures on mobile devices. To respond to these events, we'll use event listeners. Event listeners allow you to specify a function called a callback that executes whenever the specified event occurs on the element. Inside the callback, we can get the content of a DOM element via the inner HTML method. This returns a string and, for safety reasons, we can parse it into a number first. Then, we'll simply update the content of the header. Even though this is a very basic example, I hope you can see the appeal of moving some of the business logic from the server into the browser. As a quick exercise, let's also add a decrease button inside index.html. The logic should be straightforward. Increase will add 1 to the counter, while decrease will remove 1 from the counter. We have to be able to differentiate between the buttons programmatically, so the easiest approach is to add a unique ID for each of them. Then, in main.js, since we expect multiple button elements, we'll start by replacing the query selector method with the query selector all method. This method returns a node list object which contains our buttons and exposes a for each method we can use to iterate through the elements and register a click event listener. I will also extract the callback function and assign it to a constant. Note that JS is a functional language, so you can assign functions to variables, pass them as arguments, and even return them from other functions. Next, let's dive a bit deeper and explore further the world of event handling, browser APIs, and DOM manipulation. The To-Do app is the hello world of web development, so it is a must for any course. Our JavaScript will be in charge of building all the DOM elements required to manage our tasks, so the index.html page will simply contain an empty app shell and a script tag pointing to our front-end logic. So when the browser receives this HTML, it'll simply display a blank page on the screen until the JavaScript is executed. Inside the script, the first thing we'll do is to add in the app skeleton in the DOM. I'm using the getElementById function to identify the app shell, and I will update the element's inner HTML with an empty task list and an add button. Note that JavaScript supports template literals via backtick characters. This allows us to format our multi-line strings and use string interpolation, as you'll see in a second. At this point, if a user accesses our page, they'll see an add button which does nothing, so let's change that. Back in the JS file, I'll define an empty list where I'll store all my task objects and will grab the task list and button from the DOM. Note that I'm using the query selector method here, which supports CSS selectors, allowing me to target elements in powerful ways. As a convention, I like using the $sign in variable names referencing DOM elements. This is useful since these objects expose APIs to change their appearance, content, position in the DOM structure, or interact with its parent or child nodes. Next, we have to register a click event for the add button. Inside the callback, the first thing I'll do is to push a new empty task inside our to-dos list. A couple of things to note here. First, I am using object literals to define my task objects. JavaScript supports classes, so I could have defined a task class and then instantiate objects of that class whenever the add button is clicked. However, object literals are simpler and more lightweight for this use case. One downside is that since JavaScript is not a strongly typed language, using object literals means there's no enforced structure for the task objects. This can lead to inconsistencies if tasks are created incorrectly or if properties are missing. We'll solve this in the next chapter when we'll discuss TypeScript in more detail. Second, this is the first time we are using one of the many web APIs available in the browser. The Crypto API provides a secure way to generate random values, which I'm using to ensure that each task has a unique identifier. Finally, we call the render method, which is in charge of populating our DOM. Here, we'll simply iterate through the list of to-dos, and for each one, we'll define a new list entry with a checkbox input associated with the done value, a text field associated with the task title, and a text area associated with the details field. We'll also store the unique task ID as a data attribute in the DOM, since we'll need it a little bit later. This content will then replace the inner HTML of our list element. Quick disclaimer, I know that this probably isn't the most efficient implementation, but in my opinion is the cleanest one. Of course, we could append new DOM elements in the list instead of regenerating the entire list on every render, but our approach is a bit more declarative and ties in nicely with the discussions we'll have when we look at front-end frameworks. So, to reiterate, every time the Add button is clicked, a new task object is added in the to-do array, which is then traversed to generate the associated HTML. This HTML is added in the DOM, and the browser will display it in the page. However, our app doesn't do a lot at the moment, so we have to change that. First of all, we want to update our to-do object whenever the status, title or details are changing. If we were to follow the same approach we had with the Add button, where we register the event listener directly on the element itself, we would have to get all the elements in the page after each render, iterate over them, and then assign a listener for each individual input. In a list with 30 tasks, we would end up having 90 listeners. This is not really optimal, and there is a far better way to handle things. But first, we need to discuss event bubbling. This is a mechanism in which events triggered on a child element bubble up through its parent elements all the way to the root of the DOM. This means if you click an input inside a list item, the event not only fires on that input, but also propagates to its parent elements, such as the list item, the list itself and beyond, unless explicitly stopped. This bubbling behavior allows us to implement a more efficient approach called event delegation. Instead of attaching individual event listeners to each input or button, we can attach a single listener to a parent element. In our case, let's register a change event on the actual tasks list, which is an element always present in the DOM. Here we can identify the actual element which fired the event with the target property. Let's look at our HTML structure again. So we have a list entity containing list entries with inputs and text areas. When a user changes the value in the title input, a change event will be triggered on the input. Then, the element will bubble up to the list entry, and then will bubble up to the actual list group. Here, we catch the event, and the event target will point to that title input. Then, we'll get the ID of the task we are changing and the actual field we are modifying. After that, we'll look for the task entry in the to-do list, and, once found, we'll update the actual object with the new value. We should probably spend a bit more time on this code line. First, object literals support both dot notation and square brackets notation to access object fields, so both these statements are valid. In our case, the key is the class name associated with the input, which coincidentally matches the object key. Second, we are using the value property for inputs and text areas and the checked property for checkboxes. Okay, now this starts to look like an actual to-do app, but we can make a few small adjustments to achieve some big improvements. For one, right now, if the page is refreshed, all the tasks are lost. A new request is sent to the server, the app shell is returned, and when the script is evaluated, the to-do array is initialized as empty again. If we want to persist the app state, we have two options. We can save the data either on the server in a database or in the browser. We'll implement both methods. Another great API exposed by browsers is local storage. This allows you to store and retrieve data in a very straightforward key-value format. We'll perform these operations in two key moments, which fire special events. When the user closes the page, the tasks are serialized as JSON and stored locally. And when the page is opened and the initial DOM is loaded, we'll retrieve those tasks, parse them, and assign them to the to-do's global variable. Now, if we refresh the page, our task list will stick. Just a second ago, I mentioned a very important concept: global variables. All the variables and functions declared in our to-do file are defined in the global scope. In JS development, this is considered a bad practice since global variables can lead to name collisions, unintended access or memory leaks, especially in larger or more complex applications. You can test this by opening the developer console and typing in window.todos or simply todos. The easiest way to avoid polluting the global scope is to encapsulate your code inside a function or a module. JavaScript has function scope, so we can use an immediately invoked function expression to wrap all our code. The function will execute immediately, creating a private scope for our variables and functions. A more modern approach is to use JavaScript modules. With ES6, we can split the code into separate files and explicitly define what should be shared across them using exports and imports. We'll discuss modules in more detail in upcoming chapters, since this is the de facto solution to structure JavaScript apps. Going back to persisting our tasks, we can also use the server if we want our data to be shareable across multiple devices. To do so, we can simply replace our local storage calls with fetch API calls, which will trigger a sync request to the server. When the user exits the page, we'll send a put request with the data to a server URL. When the page is opened, a get request is sent to the server to retrieve and populate the to-dos. This is an interesting use case to analyze in our browser server diagram. So when the user opens the page, an initial get request is sent to the server to retrieve the index.html. Then the HTML is received and parsed. When the JS script is found, a background GET request is sent to the server to retrieve the JS file. Once the JS file reaches the browser, it is analyzed and all event listeners are registered. The HTML parsing is complete, the DOM is mounted, and the DOM content loaded event is fired. This launches yet another GET request to the server to the to-dos endpoint. Note that this is an async request, so the user can still see and interact with the page in this process. Then, the tasks are returned from the server as JSON, parsed, and used to update the DOM. In this chapter, we looked at some basic use cases while exploring the basics of web development. We've touched DOM manipulation, event handling, web APIs, and some of the most important aspects of the JS language. You are slowly mastering the lost art of vanilla JS development. All jokes aside, these concepts and processes are automatically handled by modern frameworks, but, as you'll see in the next chapters, understanding them will help you be more efficient in those frameworks. JavaScript is by far the most used programming language in the world, mostly because of its apparent simplicity and the low barrier of entry. After all you need is a browser and some basic programming knowledge, and you can immediately start playing around with the language. However, what differentiates an experienced web developer from what people call script kiddies is their understanding of JavaScript's quirks and power. Experienced developers don't just write code that works, they build code that performs well, is secure, and stands up to future changes. JavaScript's flexibility is a double-edged sword. While it lets you do amazing things quickly, it can also lead to confusing bugs and inefficient practices if you're not disciplined. So in this chapter, we'll dive deeper into the JavaScript concepts you really need to know to build good software. We'll begin by reviewing the basic building blocks and work our way up to some advanced features and general programming concepts. Expressions are JavaScript code snippets that result in some sort of value. So the hello string produces hello, 1 is greater than 2 produces false, and this array pop produces the 1 value. Expressions can be as long or as complex as needed, they can contain other expressions, and they don't necessarily change state. So, in the 1 plus 2 bit, we actually have the sum as an expression, 1 as a separate expression, and 2 as another expression. To reiterate, anything that results in some sort of value is an expression. Statements are the building blocks of any JavaScript program. Basically, each statement makes the computer perform an operation. In a practical example, this would tell our computer to assign the value 5 to the x variable, while this tells you to throw an exception. Equality versus strict equality is probably the most common question in interviews for entry-level positions. In order to test for equality, you can use 2 equal signs or 3 equal signs. The difference is pretty straightforward. While the double equal operator only compares values, the triple equal operator compares both value and type. So the number 10 is equal to the string 10, but they are not strictly equal. The triple equal is also known as the identity operator, but keep in mind that in other programming languages, identity implies that the compared values are references to the same object, meaning that both variables are pointing to the same space in the heap or the stack. As a best practice, try writing your code in a manner in which you should only be needing the strict equality operator. This discussion can be extrapolated to JavaScript's dynamic typing. In dynamic typing, a variable can hold any type of data, and that type can change at runtime. This gives you flexibility, but it also means you have to be extra cautious. You need to be aware of what type of data you're working with at any given moment to avoid unexpected behavior. Var versus let versus const is probably the second most common question in JavaScript interviews. These are keywords allowing you to declare variables in your code. Let allows you to reassign the variable later, while const doesn't. Do not confuse const values with immutable values, since a property of a const object can still be reassigned. Var also allows you to declare variables, but your declarations will have the wrapping function as their scope. Scope determines the accessibility or visibility of variables. There are 3 types of scopes in a JavaScript program: global, function, and block. On top of that, there is a 4th variation called the lexical scope we'll look into as well. To clarify things, let's take a quick look at the following situation. In a plain JavaScript file, we are defining a function called notifying active users. Inside this function, the inactive users are assigned using a const, and then the list is iterated. The forEach construct accepts a function as an argument where we are simply sending the notification message. So let's see what the scopes are here. The link variable is defined as a const, so its scope is bound to the if block. The if block is defined in the forEach function, and that's the function scope. Whenever the forEach function is executed, it has access to its outer scope as well. This could be another function scope or the global scope. The outer environment is called the lexical scope, and you should keep this in mind because we'll get back to it in a few minutes when we'll discuss closures. Finally, if the file would be imported as it is in a browser, the user's constant and the notifying active users functions would be declared in the global scope. The global scope is considered one of JavaScript's many pain points, and it is advisable that you avoid polluting it with too many of your custom variables and functions. One easy way to keep the global namespace clean is to use immediately invoked function expressions, which are functions that run as soon as they are defined. Hoisting is another interview favorite when it comes to JavaScript implementation details. The JavaScript interpreter splits the declaration and the assignment of functions and variables, and it hoists declarations to the top of their containing scope before execution. This applies to all var, let, and const variables, but var values are also initialized with the undefined value. In such situations, our variables are in the temporal dead zone, which starts at the beginning of the variable enclosing scope and ends when it is declared. Accessing the variable in the TDZ throws a reference error, and since we are discussing JavaScript head scratchers, here is another gem, the this keyword. This is one of those aspects of JavaScript that can feel a bit elusive because its value is determined by how a function is called, not by where it's written. In an object method, this references the object. Alone, this references the global scope, and in a function, this references the global object as long as you are not running in strict mode. In the strict mode case, this is undefined. Since the this keyword can point to different entities when inside a function, you can use the call and apply methods to enforce a specific function context, or use the bind method to get a new function definition correctly bound to a specific object. The context of this is why you saw a lot of bindings when defining event handlers, and this is also the reason arrow functions were introduced in the language. Arrow functions were introduced in ES6 to make function syntax more concise and to fix some of the confusion around the this keyword. Unlike regular functions, arrow functions do not have their own context. Instead, they inherit it from the surrounding code where they are defined. This is the lexical scope we looked at earlier, so the value of this is determined by the context in which the arrow function is created, not how or where it is called from. Before moving to some more interesting language features, we need to clarify two JavaScript concepts we just mentioned: strict mode and ES6. Strict mode helps you write cleaner and safer code by eliminating silent errors and enforcing stricter parsing rules. It was introduced in ECMAScript 5 to catch common mistakes early, making debugging easier. To enable strict mode, you simply add useStrict at the beginning of a script or inside a function. In a practical example, without strict mode, JavaScript would automatically create a global variable x, even if it wasn't explicitly declared. In strict mode, this throws an error, helping you avoid accidental global variable declarations. On top of that, strict mode can also prevent the use of reserved keywords for future versions of JavaScript, disallow duplicate parameter names in functions, and block the use of the this keyword referring to the global object in functions. Originally, JavaScript had irregular updates. The first few versions were released quickly, but after ES3, there was a long gap before ES5. As we already saw, ES5 introduced several important improvements like strict mode, JSON support, and better array methods. Then came ES6, also known as ECMAScript 2015, which was the biggest update in JavaScript's history. It introduced let and const, arrow functions, template literals, classes, and modules. Since 2015, JavaScript has adopted a yearly release cycle, meaning that every June, a new ECMAScript version is finalized. These updates are usually small and incremental, making JavaScript development more predictable. If the ECMAScript versus JavaScript difference is confusing, remember that ECMAScript is the official standard that defines how JavaScript should work. Back to the actual language features, one of the most powerful language constructs are object literals. This is a very flexible and efficient way to declare data structures using a list of key-value pairs separated by commas and placed inside curly braces. The object literal notation ties in nicely with some other DX goodies. This structuring allows you to extract values from arrays or objects and assign them to variables in a more concise way. Instead of manually accessing object properties or array elements, you can unpack them in a single line. The spread operator, on the other hand, expands elements of an array or properties of an object, making it useful for copying, merging, and modifying data. Of course, objects can also be created using the new keyword and the constructor function, which leads us to another particularity of JavaScript, the prototype chain. Each JS object has a private property which holds a link to another object called its prototype. Via this relationship, object inherits state and behavior from their parent prototypes. Every prototype object has a prototype of its own, and so on, until an object is reached with null as its prototype. By definition, null has no prototype and acts as the final link in the prototype chain. Because it is possible to mutate any member of the prototype chain or even swap out the prototype at runtime, this architecture decision can lead to a lot of unexpected behaviors, and it is considered a JavaScript weakness by most people. However, the prototype inheritance model is more powerful and flexible than the classical one. Therefore, even though better class support was added in the language over the years, these new class features are still built on top of prototypes. I mentioned classes which were introduced in ES6 in an attempt to bring JavaScript closer to what the community expected from a modern programming language. Before ES6, you had only the new operator and plain functions acting as constructors as options for object-oriented programming. Encapsulation was possible by employing various function scoping strategies, and inheritance was very obviously linked to prototypes. Now, you can have access to keywords such as class or extends, you can define proper constructors, getters, setters, and private fields. On top of that, we gain access to the proxy and the reflect APIs, which allow us to intercept object operations, understand, and alter their structure. While the language popularity increased, we started seeing more helpful features and constructs added in the language. Template literals are such an example. For a long time, JavaScript only allowed string declarations using the double and the single quotes. With template literals, we can refactor this code, use backticks instead of quotes, add interpolation using the $sign notation, and leverage new line support for an overall better result. Next, let's discuss the async capabilities of JavaScript. Most of the time, when you are working in the browser, you are planning and developing for various events that might happen in the future. Think here of listening to the browser events, accessing device features, or receiving server responses. The most basic solution for such scenarios is to use callbacks. But when apps grow in size and the server-client communication becomes more complex, you can run into bad programming patterns like the callback hell. A better alternative is to use promises. The promise object represents the eventual completion or failure of an async operation and its resulting value. The promise API is straightforward and pretty self-explanatory. It's important to know that these objects can be changed, and there are various utility functions such as promise all or promise any you can leverage to control the data flow. Most of the time, a good solution will not perform well in all scenarios, and this is the case with promises and nested callbacks. For the situations where a promise execution depends on the response from a previous promise execution, we can refactor the code and use async await to remove some of the clutter from our code base. There is one small issue I want to clarify here. The documentation states that using await pauses the execution of its surrounding async function until the promise is settled. Note that this doesn't mean your code will become synchronous. Async await is just syntactic sugar, and the underlying implementation is still non-blocking and fully asynchronous. While not that common in day-to-day use cases, we should briefly mention generators. These are a powerful feature allowing functions to be paused and resumed. Unlike regular functions, which execute from start to finish in a single run, generators allow you to yield values at different stages and resume execution when needed. This makes them particularly useful for handling asynchronous workflows, lazy evaluation, and iterating over large datasets without consuming too much memory. As JavaScript applications became more complex, developers needed better ways to handle missing or uncertain data without writing long chains of if conditions. Optional chaining allows you to safely access deeply nested object properties without manually checking if each level exists. Nullish coalescing, on the other hand, helps with setting default values only when a variable is explicitly null or undefined. Unlike the OR operator, which treats any faulty value as invalid, nullish coalescing ensures that only truly missing values get replaced. This is especially useful for distinguishing between an empty user input, which should be allowed, and a missing configuration setting, which needs a default. JavaScript also has built-in data structures to enhance performance and readability. Set provides a way to store unique values, eliminating the need for manual duplicate checks in arrays. Map is an optimized key-value store, offering faster lookups compared to plain objects, especially when working with a large number of keys. Unlike objects, which can only use strings or symbols as keys, map allows keys of any type, including functions and objects. Weak map and weak set extend these structures by allowing keys to be garbage collected when they are no longer referenced elsewhere in the code. This makes them ideal for managing temporary metadata, caching, or tracking objects without preventing them from being cleaned up. On a more higher level, functional programming is one of the most appealing parts of JavaScript. There are a lot of debates about the best programming paradigm, but it is my experience that in real-world projects you'll end up using both functional and OOP concepts. So, a language that offers you the option to follow basic object-oriented principles while also providing various functional constructs and syntactic sugar is going to be more appealing to developers. JavaScript supports first-class functions, which means there are no restrictions on their use, and functions can appear anywhere in a JavaScript program. So you can assign a function statement to a value, you can pass it as a parameter to another function, or you can have it defined as a return type. Functions that work with other functions, either by receiving or returning them, are called higher-order functions. This flexibility gives you access to a lot of different expressive ways to write your code. You can, for instance, compose the add and square functions into a resulting function, or if you are feeling fancy, you can use currying. This is a more advanced technique that transforms a function from a callable of some x and y into a callable of sum of x and of y. Closures are a concept closer to the reality of everyday projects, and the chances are you've been using them without actually realizing it. They are a combination of a function bundled together with references to its surrounding state. In other words, a closure gives you access to another outer function scope from an inner function. It is also worth mentioning that JavaScript supports tail call optimization, which is a technique used to optimize recursive functions by eliminating unnecessary function calls. Normally, when a function calls itself, a new stack frame is created for each call, which can lead to Stack Overflow errors if the recursion is too deep. However, in tail call optimization, if the recursive call is the last operation performed in a function, also known as a tail position, JavaScript engines can optimize it by reusing the current stack frame instead of creating a new one. The language features are just part of the story. The JS code is then executed by a JavaScript runtime, which uses an engine such as Chrome's V8 or Mozilla's SpiderMonkey to convert JavaScript into machine code. The engine itself consists of a memory heap and a call stack. The heap stores all the variables defined in our code, while the stack is in charge of keeping track of the function's execution. JavaScript is single-threaded and uses an event loop to monitor the stack. Whenever the stack is empty, the event loop checks for any additional work in the callback queue. This architecture makes JS asynchronous and non-blocking. In other words, whenever the runtime has to wait for a long-running operation, like an HTTP GET request for instance, the callback which has to be executed when the response is received will be added in the callback queue, and the runtime can continue its work until the response data is available and the stack is not occupied with some other task. Besides the engine, the event loop, and the callback queue, JS runtimes also offer a large set of web APIs you can use to achieve various tasks. This is how you can interact with the DOM, geolocate your user, spawn a new web worker, or retrieve information back from the server. All these things are working together when your code is executing. Let's review the whole process by looking at an example. I'm defining a simple callback function, which fetches a user and some user details, then populates them in the DOM. When the user clicks on the button, the callback is added in the queue. Then, when the stack is empty, the event loop will move the callback from the queue to the stack. The code will be executed line by line, and when the fetchDetails function is reached, a new entry will be added to the stack. Inside this function, we are making a call to the server using the fetch API. The request is being triggered and, at this point, the runtime doesn't care about this execution thread anymore. It pops the fetchDetails function of the stack and returns into the populateDetails function. Here, the callback code will be ignored because it relies on a server response from the fetch API container. This callback will be executed only if and when we'll get back the response. Then, the populateDetails function is popped off the stack, and now that the stack is empty, the event loop can delegate more work. Next, let's assume a few seconds passed and the fetch API call finished its execution with a successful result. At this point, that callback code that was previously ignored is pushed to the callback queue. The queue is a first-in, first-out data structure, so, of course, the callback will not be executed immediately. However, when its turn comes and the stack is empty again, the callback will be moved to the stack, and that code will then be executed following the same process we already described. Now that we've reviewed this architecture, it's worth noting that the task queue is actually divided into two separate structures, a callback or macrotask queue and a microtask queue. The callback queue is where standard asynchronous operations like setTimeout, setInterval, and input-output tasks, such as fetching data from an API, are queued. These tasks are scheduled by the runtime and executed only when the call stack is empty. The microtask queue, on the other hand, contains high-priority tasks, such as promise callbacks, mutation observer callbacks, and queue microtask functions. Remember that microtasks always run before macrotasks when the call stack is empty. This means that if you schedule both a promise resolution and a set timeout, the promise callback will execute first. On top of that, there are some other implementation details and rules you need to know in order to write efficient, non-blocking JavaScript applications. Microtasks will run immediately after synchronous code finishes, but before macrotasks. If a microtask creates another microtask, it runs before the event loop moves on, and a single iteration of the event loop always processes all pending microtasks before moving to the next macrotask. If this sounds too complex, don't worry. The chances of you running into these details in your day-to-day job are pretty slim. As we've seen in previous chapters, JavaScript's dynamic nature gives it flexibility, but that same flexibility can lead to hard-to-debug errors, inconsistent codebases, and a lack of clear structure in larger applications. This became a real problem in the past 10 years, since SPAs increased the complexity of JavaScript codebases. The strongly typed model of TypeScript was introduced as a solution to these problems. By providing static type checking, better ID support, and a structured approach to JavaScript, TypeScript makes it easier to build and maintain large applications. Unlike other languages that enforce types at runtime, TypeScript is fully compiled into JavaScript before execution. This means TypeScript doesn't introduce new features to the runtime environment, it simply helps developers catch errors earlier, write more maintainable code, and take advantage of modern tooling. In order to use TS, we need to first install it and set up a simple development environment. It is important to note that our development process will change quite a lot. If previously, all we had to do is to write our JS code in a JavaScript file and serve it directly in the browser, the process now requires an additional compilation step before the code can run. Since TypeScript is not understood by browsers natively, all .ts files must first be transpiled into JavaScript. So our new development workflow has 3 steps. First, we write our code in .ts files. Then, an external runtime like Node.js runs the TypeScript compiler that compiles our .ts files into .js files. Finally, the browser executes the generated JavaScript file. Quick side note, I just explained the process of compiling TS into JS since this is needed to run your code in the browser. However, there are numerous other runtimes like Deno, Bun, and even Node with the strip types flag that offer first-class TypeScript support. What's also appealing beside type safety is that the TypeScript compiler can help with other common tasks required in front-end development. Modern JavaScript applications are built using modules. These are files that export and import code to keep projects organized. TypeScript fully supports these ES modules and will do all the heavy lifting for you. Without TS, managing modules in a large JavaScript project can quickly become a nightmare since developers have to rely on manual checks to ensure that imported functions and objects are used correctly. By default, TypeScript compiles each .ts file into a separate .js file. However, in production, it's often better to merge everything into a single bundled file to improve performance. The outFile tsconfig property tells TypeScript to merge all compiled JavaScript into bundle.js, reducing the number of network requests. On top of that, TS can be paired with a minification tool like Cursor to remove whitespace, comments, and unnecessary characters to reduce file size and improve performance over the wire. The most important aspect of TypeScript, however, apart from type safety of course, is that it can convert modern JavaScript features into versions compatible with older browsers. We discussed JavaScript versioning and its yearly release schedule earlier. When a new ECMAScript version is released, the browsers have to update their JavaScript implementation accordingly, but this usually takes time. So, developers cannot assume that all users will have browsers that support the latest ECMAScript features. This is where TypeScript's transpilation comes into play. It allows you to use modern JavaScript features such as optional chaining and transpiles your code under the hood into JavaScript code that older browsers can understand. Now that we are familiar with the basics of how TypeScript integrates into our development workflow, let's explore one of its most important features, type annotations. TypeScript allows you to explicitly define the type of a variable, function parameter, or return value. This ensures that variables hold only the expected kind of data, reducing the likelihood of type-related bugs. As you should know by now, in JavaScript, you can assign any type of value to a variable. This flexibility can cause issues because age was first assigned a number but later reassigned a string. If this variable is used in a calculation later in your logic, the code might fail in unexpected ways. In TypeScript, however, you can explicitly declare the type. This ensures that age will always be a number, preventing accidental assignments of the wrong type. Note that TypeScript is smart enough to also infer types when possible, so, in practice, you'll probably write your code like this. Types might not look like much, but they are drastically improving the reliability and stability of your code. In real-world scenarios, you'll run into situations when variables need to hold multiple types. This is when union types come into play. If you find yourself using the same union type repeatedly, you can also define a type alias. When it comes to types, there is one rule you should always follow. Avoid using the any type at all costs. The any type might seem appealing at first, but it completely defeats the purpose of using TypeScript in the first place, since it essentially turns TS into plain JS by disabling type checking for that particular variable. In practice, there will be those corner case scenarios where you don't really know the shape of an object. The API you are consuming might return an unknown value, a third-party library might not have type definitions, or you are forced to work with some JavaScript modules in your TypeScript project. In such scenarios, don't hesitate to use union types and type guards to make your code safer. So remember that whenever you are using any, you are weakening the type safety of your program and experiencing unexpected runtime errors, reducing the maintainability of your codebase due to unclear type information, and losing the auto-completion and refactoring support provided by your IDE. If you are truly unsure of a variable's type, you could use the unknown type instead of any, or leave out the type reference to allow TypeScript to infer it. The unknown type requires explicit type checks before the variable can be used, which helps reduce the risk of runtime errors. You could also go in the opposite direction and make your type system too complex. Remember to avoid overly verbose type annotations when they are unnecessary. So, instead of manually specifying types that can be inferred, allow TS to do its job. Overcomplicated types are a common pitfall in TypeScript projects, and although complex types may occasionally be needed, making them overly complicated can result in confusion, reduced readability, and higher maintenance costs. Furthermore, developers may find themselves spending more time deciphering these types than focusing on actual business logic, which can lead to slower development cycles. Simplifying types and focusing on clarity can help create a more maintainable codebase and improve collaboration among team members. So here are a few things to keep in mind. Avoid nested types since they are hard to read and maintain. Avoid complex union and intersection types since they can lead to convoluted and difficult to understand types. And don't overuse mapped and conditional types since they can easily get overcomplicated. TypeScript offers a strict mode compiler option that enforces more rigorous type checking and constraints to enhance code quality and to catch potential issues during development. You can enable this by setting the strict flag to true in the tsconfig file. Strict mode is a combination of several individual type checking options, collectively aimed at making your TypeScript code safer and more reliable, ranging from disallowing you to use the any type to enforcing strict mode in the resulting JavaScript files as well. Interfaces are another core component in TypeScript. You can use both mechanisms to define custom types, but there are a few key differences you should keep in mind. A type alias creates a new name for a type. This can be a primitive, union, intersection, tuple, or any other type. In other words, it can represent complex structures and give you flexibility in defining types that go beyond simple object shapes. On the other hand, interfaces are primarily used to define the structure or shape of an object or class. Interfaces in TypeScript are more focused on describing the properties and methods that an object should have, and they provide a powerful way to enforce the structure of objects across your codebase. As a result, you should use interfaces for object shapes and class contracts, use types for complex and flexible structures, and use a combination of both to create powerful type definitions. Of course, you should be consistent. Once you choose between interfaces and types based on your specific use case, you should stick with this decision across your codebase. And, just like I explained at the beginning of this video, types and interfaces exist only at compile time and do not have a runtime representation. Now that we have a solid understanding of TypeScript's type system, let's explore some advanced concepts that will help you write more maintainable, scalable, and efficient TypeScript code. These concepts may seem more complex at first, but once you master them, they will significantly improve your workflow. While union types allow a variable to be one of many types, intersection types allow a variable to be a combination of multiple types. This is useful when merging different data structures or enforcing multiple constraints. Another concept that's widely used in TypeScript is discriminated unions. These are especially useful when handling multiple possible states in a type-safe way. The key idea is to include a shared literal property, usually called a discriminator, so TypeScript can automatically narrow down the type based on its value. This is an extremely powerful pattern, particularly when dealing with API responses or application state. Mapped types, on the other hand, allow you to dynamically create new types by modifying properties from an existing type. This is useful for scenarios where you need to enforce read-only, optional, or required constraints dynamically. Another incredibly powerful feature is template literal types, which allow you to dynamically construct string-based types. This is particularly useful for cases like CSS class names, API routes, or UI component variants, where a combination of predefined values needs to be enforced. While templated literal types let you dynamically generate strings, conditional types let you define types dynamically based on conditions. This is where TypeScript starts to feel almost like a programming language within a programming language. At this point, we've covered a lot of ground. You now have a deep understanding of how TypeScript can improve code quality, reduce bugs, and help you structure complex front-end applications. Next, we'll put all the TypeScript, JavaScript, HTML, and CSS knowledge to test in a real project. Okay, at this point, you should have a good understanding of the building blocks required in front-end development. HTML gives you structure, CSS makes it look decent, and JavaScript brings everything to life. The client communicates with the server to exchange information, and you can build modern user interfaces and experiences through DOM manipulation and various web APIs. You also saw how to work with these technologies directly, but in the real world, you rarely build everything from scratch. In real-world projects, working directly with vanilla HTML, CSS, and JavaScript quickly becomes tedious, error-prone, and hard to scale. That's where front-end frameworks come in. As your app grows, so do the number of components, states, user interactions, and data flows. Suddenly, keeping track of what changes when, or manually updating the DOM starts to feel like herding cats. So you start running into problems that every developer has already faced 1,000 times before. There is nothing magic about frameworks. They're just tools that automate a lot of the repetitive, error-prone work we already discussed. They help you update the DOM efficiently, managing component state, handling routing, optimizing re-renders, batching updates, and maintaining a consistent structure across the app. It's also important to remember that knowing how to use a framework doesn't absolve you from having to know the fundamentals. In fact, the more comfortable you are with the fundamentals, the easier it is to actually understand what a framework is doing behind the scenes. You'll be able to troubleshoot weird bugs, avoid unnecessary re-renders, and build custom behavior without relying on third-party hacks. Frameworks are abstraction layers, and like with any abstraction, they make common things easier but complex things harder if you don't have a good understanding of the things you're abstracting away. On top of that, the fundamentals and common workflows you've learned are exactly the problems every front-end framework is trying to solve. So even though people complain about framework fatigue and the overwhelming number of libraries out there, the truth is they all share the same core concepts. If you understand those concepts, you'll be able to easily become productive in any framework you choose. When you really distill things down, modern web apps are built as a collection of components. Each component has three main responsibilities. First, it manages some sort of internal state which is either passed down from parent components, captured from user input, or directly retrieved from the server. Then, it uses this internal state to render the DOM, detect changes, and keep the UI in sync with its associated data. And finally, it reacts to changes triggered from these DOM elements and either handles the event internally or it passes it up to one of its parent components. You'll notice that one way or another, all modern front-end frameworks are built to solve these exact problems. What might surprise you is how similarly they go about it, since most of them rely on the same underlying mechanisms to implement their solutions. We'll start by quickly reviewing the current front-end framework space and then spend some time building a small app with one of these frameworks. We can identify 4 types of frameworks these days. First, you have the big 3, which are established solutions widely adopted on all fronts. These enjoy amazing community support and they are probably your safest bet in the job market. Second, you have a new wave of frameworks which aim to fix the pain points of the older ones. These focus on performance, DX, and often leverage newer browser capabilities or technical concepts. They're gaining traction fast, but they're not yet as mature or widely adopted. Third on the list, we have the meta frameworks. These are built on top of the core frameworks to handle things like routing, server-side rendering, static site generation, and deployment. The chances are you'll actually use a meta framework when starting a new project, mostly because it abstracts away a lot of the setup and boilerplate that would otherwise slow you down. And finally, I have to mention solutions like Alpine, HTMX, or PrettyView, which take a different approach entirely. These libraries aren't full frameworks in the traditional sense. They're lightweight tools designed to enhance static HTML with small bits of interactivity without requiring a full client-side rendering setup or a build step. If you recall, we discussed SPAs versus MPAs at the beginning of this course. While the first 3 categories lean heavily into the SPA model, where JavaScript runs the show on the client side, these lightweight libraries are a better fit for enhancing traditional MPA architectures. They bring interactivity to otherwise static pages without introducing the overhead of a full framework or the complexity of a client-side router. Okay, next, let's quickly review the strengths and weaknesses of these frameworks. Note that this is just an overview aimed to give you a quick idea about the options you currently have in the market. As I already said, these frameworks will behave the same in probably 90% of the use cases, and these days it simply boils down to your preferred dev experience and job opportunities when picking a framework. As they say, the best tool for the job is the tool you know best, so don't worry too much about picking the right framework. As long as you master the fundamentals and you have a decent understanding of the framework abstractions, any of the following options will be a good fit for you. React is by far the most used framework. It is backed by Meta, it has a huge community, lots of jobs, and a massive ecosystem. On the downside, it is not opinionated, which means you'll need to make a lot of choices yourself, and codebases might look quite different depending on the preferences of the involved developers. On top of that, managing side effects and the rendering process can quickly get messy if you don't fully understand how React's rendering model works. Concepts like hooks, re-renders, memoization, and state synchronization are powerful but not always intuitive, since React is the only modern framework using a legacy system to detect changes and update the DOM. The React compiler aims to fix some of these issues by automating memoization and optimizing re-renders behind the scenes. Vue is generally easier to pick up, especially if you're coming from an HTML and CSS background. Its syntax is more approachable and the framework is more opinionated than React. This means there's usually a clear Vue way to do things, which makes team collaboration smoother and reduces decision fatigue. Vue also offers fine-grained reactivity and solid performance, especially in Vue 3. The documentation is excellent and the developer experience is polished. On the downside, the job market for Vue isn't as big as React's, especially outside of specific regions. Angular is a different beast. It's a full-fledged framework built and maintained by Google, with everything included ranging from routing, forms, HTTP, dependency injection, and more. It's TypeScript first, very structured, and great for large-scale enterprise apps where consistency and maintainability are critical. But with all that power comes complexity. The learning curve is steep, and Angular tends to be more verbose than React or Vue. You don't just write components, you deal with modules, decorators, services, and a fair amount of boilerplate. What's really interesting though is that the Angular team understood that its complexity is a problem, and in recent versions it's been quietly trying to fix that. Standalone components were introduced to cut down on boilerplate and reduce the need for ng modules. On top of that, signals were added to offer a more intuitive reactivity model, similar to what developers are used to in other frameworks like Solid or Vue. Switching gears to some more modern approaches, Svelte shifts heavy lifting to compile time rather than runtime. It compiles components into efficient code that directly updates the DOM instead of using a virtual DOM, resulting in better performance and smaller bundles. Its clean, readable syntax requires less code. Trade-offs include compiler-first patterns that differ from React or Vue and a younger ecosystem with fewer integrations, jobs, and resources. However, Svelte Meta Framework has matured significantly, offering routing, SSR, and file-based routing capabilities. Solid follows a similar compiler-first approach to Svelte, but maintains a React-like syntax and mental models. It creates highly optimized code that updates only what changes without using a virtual DOM or diffing algorithm. Instead, it uses fine-grained reactivity that tracks dependencies at the statement level, resulting in exceptional performance and minimal re-renders. On the downside, it includes a smaller ecosystem than established frameworks and fewer learning resources. While growing rapidly, the job market remains limited compared to the established solutions. Qwik, on the other hand, revolutionizes the norm by focusing on resumability rather than hydration. While traditional frameworks need to download, parse, and execute JavaScript before becoming interactive, Qwik serializes the application state directly into HTML and resumes where the server left off. This eliminates the expensive hydration process, resulting in near-instant interactivity regardless of application size. The framework delivers impressive performance metrics, with minimal JavaScript shipped to the client by default, making it ideal for performance-critical applications. Its architecture supports fine-grained lazy loading at the component level, loading JavaScript only when needed for specific interactions. Trade-offs include a fundamentally different mental model that requires unlearning established patterns, a relatively new ecosystem with fewer third-party integrations, and limited job opportunities. However, as performance becomes increasingly important, Qwik's innovative approach is gaining attention in the developer community. Okay, let's see now how these frameworks work in practice. For the next few minutes, we'll build a small web bookstore application. We'll use Astro as the meta framework, and we'll pair it with Solid for the interactivity bits. Setting up the project is really straightforward. We'll simply initialize an Astro application, go through the wizard, and then add in the Solid.js integration. This is the resulting project structure, and we'll spend most of our time in the source directory. Under Pages, we'll create an index.astro file. This is where our users will end up when they reach our website for the first time. Remember that Astro uses the file and folder structure inside source pages to automatically generate routes. So index.astro becomes the homepage, and if we create something like books.astro, that will automatically map to books. So let's walk through this code. The top section is called the Astro front matter. Think of it like a setup zone where you can import components, styles, or anything else we want to use in this file. It looks a bit like a JavaScript file because it is, so you can write regular JavaScript in here, ranging from import statements to variables and even functions if you need them. It's all scoped to this component, and it runs on the server, not in the browser. That means you can safely fetch data, access environment variables, or prepare content before anything gets rendered on the screen. First, we import the layout component. This is just a wrapper to keep our pages consistent with the same header, footer, and maybe some shared metadata. It's a good way to avoid repeating yourself. The HTML content itself is really straightforward. This would be the landing or welcome page in a real project, so here you'll usually add your product sales pitch and other useful information. For this demo, however, we'll keep it really simple and render two links pointing to our authentication flows. Note that this is an Astro component, so it will be rendered on the server and the HTML will be sent to the client. No JavaScript is needed for this page to load and work. By default, Astro generates static pages, which is great for performance, SEO, and caching. But in our case, we have to render pages dynamically on every request, so we'll need to switch from server-side generation to server-side rendering. Astro lets you opt into SSR on a per page or per project basis. In our case, we'll keep things simple and we'll enable it globally in our Astro config file. This way, pages get rendered fresh every time a user visits it, so we don't need to rebuild the whole site just to show a different book name or cart value. Next, let's take a quick look at the layout, which is just a standard Astro component. Astro.props is used to receive data from the parent component. In our case, this is how we get the title from index.astro. The slot tags are a bit more interesting. These are placeholders which allow you to insert content at specific positions. The regular slot handles the main content, and the name slot head is used to inject additional meta tags or other things inside the head section. What's important here is that this layout gives us a consistent HTML structure across pages, but still lets us inject page-specific content when needed. Next, let's take a quick look at the Auth Astro component where things get a bit more interesting. Here, we import a solid component called authentication form, which is the first interactive part of our app. Note the client load directive on the component. That's how Astro knows it should hydrate this component on the client, or in other words, make it interactive after the page has loaded. This is a key part of Astro's architecture. It only loads JavaScript where you actually need it. Instead of hydrating the entire app like in a traditional single-page application, Astro lets you define islands of interactivity and sprinkle in JavaScript selectively, which keeps things fast by default. The auth form component is where we bring in Solid to handle interactivity. At the top, we set up a bit of state using Solid's create signal. We track which tab is active and store the form inputs like email, password, and name. There's also an error message signal we update if something goes wrong during login or registration. When the component loads, it checks the URL for a register parameter and switches the active tab automatically. This lets us link directly to the registration form if needed. The login and register functions follow a simple structure. They prevent the default form behavior, validate the input, and make a post request to a fake API endpoint. In a real-world scenario, this is where you'd send a request to your backend component in charge of authentication or to an auth provider like Auth0 or Clerk. If the response is successful, we store the user data in local storage and redirect to the books page. If something fails, we capture the error and display it on the screen. In the return block, we render two buttons for switching between tabs and use Solid's show component to conditionally render the name field for the register flow. Both login and register use the same form, but the action performed will be different based on the active tab property. Remember that the component is hydrated with the load directive, so it only becomes interactive on the client side after the page loads. The rest of the page stays static and fast, which is exactly what Astro is good at, sending JavaScript where you really need it. Once the login is successful, the user is redirected to the dashboard, which is the core of our little bookstore. This is where they can browse books, add them to the cart, or borrow them. Let's break down what's happening behind the scenes and walk through the code. The Astro file loads the layout component, which we already covered, and within that layout, it renders a bookstore solid component. Note again the client load directive, which tells Astro to render the surrounding structure on the server, but hydrate bookstore on the client. That means only this component becomes interactive, keeping the rest of the page fast and static. The bookstore component is written in Solid and goes through the usual steps. We start by using the create signal hook to define the state we need to keep track of which books have been borrowed and whether the cart modal is open. Next, we'll use the create resource utility to load the books asynchronously. Create resource is Solid's built-in way to handle async data while keeping your components reactive. It wraps a fetch call and gives you two things: the resource itself, which behaves like a signal, and the loading state. Behind the scenes, Solid tracks when the data is ready and automatically re-renders anything that depends on it. Then, we'll use the onMount lifecycle hook to run logic when the component is first loaded on the client. Here we can fetch the existing cart items from our local store or backend. In the template, the component starts by rendering two child components: a header, which includes the cart button, and the cart model, which is conditionally shown based on the isCartOpen signal. Nothing fancy so far, just solid component-based design. The actual book rendering happens inside a div with a booksGrid class. We use solid's show component to wait for books to be available. If the data hasn't been loaded yet, it just shows a loading message. Once the books are in, we map through them and render a card for each one. Each book card shows the image, title, author, and price. For the image, we add a simple fallback using the onError event in case the image URL is broken. This is a common pattern for user-facing apps where external assets might fail. Now, for the fun part, let's look at interactivity. Each book card has two buttons, an Add to Cart and a Borrow. We check the current state before rendering each button. If the book is already in the cart, we show a disabled button labeled In Cart. If it isn't, we show the active Add to Cart, then we apply the same logic for borrowing. Clicking Add to Cart will add this book into the cart items list. For Borrow, let's make things a bit more interesting and send a post request to the API Borrow endpoint. This is a good opportunity to discuss Astro endpoints. While this is a front-end course, remember that Astro runs on Node.js on the server, so we can leverage that to create simple server endpoints directly inside our project without needing a separate backend or a full API framework. Astro lets you create API routes by placing TypeScript or JavaScript files under the source page's API directory. The file name and its export define the route and support HTTP methods. For example, if you place a file at apiborrow.ts, it becomes available at /API/borrow. In the endpoint file, we start by exporting a post handler, which makes this endpoint respond only to post requests. In practice, you could export any HTTP verb here. Inside the handler, we await the JSON body of the incoming request, which contains the book ID the user wants to borrow. Then, we store this information in the local database and return a 200 success response. Note that this is a demo project, so we'll not focus on validation or other business logic details. So when the user clicks the Borrow button on the front end, we send a post request with the book ID and this endpoint catches it. That's the full loop. Solid handles the UI and state, and Astro gives us a backend layer to respond to those interactions. This kind of setup is perfect for learning and even for small projects because it keeps the architecture tight and easy to reason about. You don't need to spin up a backend server or deploy a separate API instance. It's just one codebase, one deployment, and one mental model. Before we wrap up this chapter, let's also take a quick look at the shopping cart modal. The cart modal solid component accepts two properties. IsOpen tells us whether the modal should be visible or not, and onClose, which we call when the user clicks outside the modal or hits the close button. Inside the component, we use createResource to fetch the full details of the books currently in the cart. We also track the total cost with a create signal, and we recalculate it automatically using createEffect every time the cart data changes. In rendering, we use the built-in show and for components to do most of the work. First, we show a loading message while the data is being fetched or if the cart is empty. Once we have books to show, we map through them and render each one with a title, image, author, price, and a button to remove it from the cart. Finally, at the bottom, we display the total price and the checkout button. Clicking Remove simply removes the book from the item store, while clicking Checkout sends a post request to a checkout endpoint. On the backend, we already talked about how these endpoints work, so there's nothing new here. We read the request body, perform some validations and business logic, then return either a success response or an error. We covered quite a lot up until this point, and that's great. But in the age of LLMs and code generation, having a really deep understanding of the tools you are using is a must. So in the next chapter, we'll build a small front-end framework from scratch. Yes, I know. The last thing this industry needs is another front-end framework. But we are not building one to change the world, we are building one so you finally understand what the hell is going on behind the curtains of the ones you already use. There are three very real reasons to go through this. First, it cements the fundamentals. In this course, we went through a lot of information ranging from DOM manipulation to reactivity to rendering strategies. Building a tiny framework forces you to tie it all together. Second, it gives you perspective. All established frameworks solve the same problems in slightly different ways. Once you understand what those problems actually are, you'll stop getting lost in syntax and start recognizing patterns. And finally, it demystifies the magic. A lot of people treat frameworks like sacred artifacts. You're about to build a framework on your own, and you'll realize it's just JavaScript. Sure, it's clever, well-structured JavaScript, but JavaScript nonetheless. So let's not waste any more time. We'll start with a simple counter app where you click a button and the number goes up. While simple, this basic behavior already requires two critical capabilities: listening for events, in this case a click, and updating the DOM when a state value changes. When you really think about it, this is the essence of every front-end framework ever built. And because the entire JS ecosystem migrated to signals in recent years, we'll base our reactivity system on signals as well. Our framework has some minimum requirements. It should offer a reactive state system based on signals, it should use a clean declarative syntax via custom attributes, it should be server-friendly so that we can delegate rendering or updates to the backend via fetch calls, and, preferably, it should be written in no more than 200 lines of code. So the implementation of our counter should look like this. It's almost readable even if you've never seen the syntax before, and that's the whole point. We're not inventing a new DSL here, we're just using attributes to wire logic to DOM elements. Attributes prefixed with a colon are reactive bindings, and we use it for event listeners. That's our entire API. In a new JavaScript file, we'll first wrap everything in an immediately invoked function expression so we don't pollute the global scope. This way we can define our own state, track internal logic, and avoid stepping on any global variables. As I said, reactivity will be implemented based on our own signal system. If you remember how Solid or Angular's new reactivity works, signals are just reactive values that notify listeners when something changes. You can think of them like fancy variables that broadcast updates. Our version is simple. Each signal keeps track of its current value and a list of functions that need to rerun when the value changes. When the signal is read, we silently register the active context. When the signal is written to, we call all those listeners. To make this work behind the scenes, we use a JavaScript proxy. This lets us intercept get and set calls on our state object. When a component binds to count, it's actually accessing a getter that quietly says, "I depend on this value, let me know when it changes." This is how we'll track dependencies without any boilerplate. Now that we've got a basic reactive state system in place, the next step is to traverse the DOM and find the elements that need special treatment. We'll basically select anything with a colon binding or a net event listener. We then loop through these elements, and depending on what we find, we wire up either a signal binding or an event listener. Let's talk about bindings first. If an element has something like text equals count, we parse the expression using JavaScript's with statement to evaluate it in the context of our reactive state. When the expression accesses a value like count, our proxy registers that dependency. From that point on, anytime count changes, we rerun the expression and update the element's text content. The same logic applies to :HTML and for any other attribute binding we decide to support. This is surprisingly effective, and it mirrors the behavior of reactive computations in frameworks like Solid or Vue. We are not diffing virtual DOM trees or using fibers. We are just reacting to specific values and updating the DOM directly. Event listeners are straightforward as well. For elements that have event listeners attached to them, we'll start by registering a global listener on the document.body. This might sound inefficient, but it's not. By delegating events at the root level, we avoid attaching multiple listeners to individual nodes, and we can support dynamic DOM updates without doing extra work. When an event fires, we check if the target has a matching attribute like click, and if it does, we run the expression in the same way as before, evaluating it with access to state. This system works not just for basic interactions, but for more advanced behaviors too. Let's say you want to hit the server when a button is clicked. Instead of writing JavaScript, you can define an endpoint directly in the event attribute like this. The framework detects that this is a URL, performs a fetch call, and once it gets the HTML response, replaces a part of the DOM with the new content. In more advanced cases, you can even specify which DOM node should be replaced using a data target attribute. This idea is heavily inspired by HTMX, and it works incredibly well for hybrid applications where you still want to render things on the server but sprinkle in interactivity. At this point, our little framework supports signals, bindings, event delegation, and fetch-based DOM updates. We've even included a special load event that fires when an element is first processed, which is basically a lightweight version of a lifecycle hook. What you'll notice while building this is that most of the magic in frameworks is just structure and conventions. We are just coordinating data and DOM updates efficiently in a simple, descriptive manner. That's what every front-end framework is doing under the hood, whether it's React with hooks, Vue with its reactivity system, or Solid with its fine-grained updates. You now understand the real reasons why signals matter, why reactive state needs to track dependencies, and why event delegation is cleaner than directly attaching listeners. You've implemented a subset of JSX behavior without ever touching Babel. And you've seen that server-rendered HTML and client interactivity can absolutely coexist in a sane, declarative way. Sure, nobody's going to use this library, but you will have a far better understanding of the ones that matter. You'll stop copy-pasting use-effect examples from Stack Overflow and actually know what's happening under the hood. If you've made it this far, congratulations! I'd love to hear your thoughts and feedback in the comments. Also, please consider liking, subscribing, and checking out my main channel for videos on programming languages, frameworks, and tech news.